Hello everyone, I am Julian Corrales. Today I'm presenting a review of Metasurface based on the article A Review of the Metasurface Psyches and Applications by Hao Thang Shen, Antoinette J. Taylor, and Nanfang Yu. Published on May 26, 2016, Metasurfaces are ultra-thin structures that control light in groundbreaking waves from microwaves to visible wavelengths. Metamaterials versus metasurfaces. Metamaterials composed of periodic subwavelengths, structures that resonantly coupled to electromagnetic fields exhibit properties not found in nature. Um, Negative refractive index. Challenge: high losses, strong dispersions, and difficult 3D fabrications. Metasurface 2D planar metamaterials with sublength thickness single on fill layers. Isol fabricating using lithographic nanoprinting, ultra-thin natural surfaces, uh, undressable losses, enable spacing, variable optical responses, phase amplitudes, and polarizations, controlling light to generalized law. Metasurface manipulates light by introducing abrupt, especially varied changes in optical properties, overcoming the limitations of bulky conventional optic. 1. Abrupt phase change. Metasurface introduce a special distribution on phase jumps by sub subwavelength resonators, opticals, antennas. 2. Generalized laws. Derived from fundamentals, principle these laws show that the interfacial phase gradients act as an affected wave vectors, bending transmitted and reflect light into arbitrary directions. 3. Waves control waves front control. Wave in general, see phase gradients, we can control direction on wave propagation and the shape of the wavefront. Wavefront shaping technicals. Pancharatnam, very phase jumps create by routing anisotropic scratch rates. Phase is a function of orientation angle, lending to ultra-broadband performance. Um, Huygens surface archives nerve unit transmissions efficient by matching metasurface impedance to free space, controlling electric and magnetic polarity, polyvarism. Flat lens and holograms. Metasurfacing posed preset face profiles to create flat lens, high focusing, and complex computer-generated holograms. Polarization conversions enhance efficiency. Metasurfaces are crucial for converting between polarization states. Linear to cycle necessity for modem communication and sensing, and one linear to circular conversions are achieved by generating two propagating waves with equal amplitudes, orthogonal linear polarizations, and p2 phase difference. 2. Multi-layers structures, field layers, metasurfaces. Your 3 layers signify the enhanced conversions efficiency and operational power throughout near field coupling. 3. Linear polarization rotation. Arched weight isentropic structures enable 19% rotations over ultra-broadband ranks, 18% offensive over 2 octaves in TAC. The electric metasurface law-loss alternative. The electric metasurface adheres to several optic losses of metallic structures, speciality of optical frequency, by utilizing low loss, high refractive index materials. My resonance in the electric particle support strong electrics and magnetic spreading, enable control over magnetic and electric responses. Loss reproductions. Demonstrate linear polarization conversion with 98% efficient in infrared, significantly surpassing metallic counterparts. Directional scraping by overlapping electric and magnetic dipole resonating back scraping can be cancelled, leading to enhanced forward scraping. Hue hence secondary source. Metasurface for wave guidance and relations. Metasurfaces are being used to control wave guidance weights uncoupled with free space weights, offering advances over conventional rating-based couplers. Holographic Leakey waves antennas, impedance surface converting surface waves into freely propagating waves with desired far fields patterns, um, circular correlations. Surface waves control, metasurface enable control of in-plane propagation and surface waves, realizing designs like Lüneburg lens and Maxwell fish eye lens. Integrate photonic phases array antennas on waveguides, create a unidirectional phase gradient for broadband robust mode conversions. Active metasurface dynamic control. Integrating functional materials allow for active control and dynamic turns of metasurface property via electrical, optical, or thermal means. Metal semiconductor hybrids and semiconductors silicon gas enable switchable or frequency tunable response by photostations or voltage by up to gigahertz speeds. Graphene hybrids and graphene tunable conductive allow high-speed electrically tunable modulation in semi-infrared and TAC ranks up to modulation depth. Fine transition materials, materials like BO2 and stove enable thermal on electric switching or resonance frequency, useful for memory designs on modulator. Future opportunities and challenge. Dispersion of flat lengths, developing flat lengths and score chromatics and monochromatic aberrations to revolution optic instrumentations and miniaturizations. Mid-ear in Tensane modulator, creating compact, fast modulator and special line modulator for communications, imaging, and remote sensing applications. Radioactive calling, designing metasurface wide exceptional thermoregulations, property for passive calling, and the structural colorization inspired by nature. New material platform exploring materials like transitions metals, nitrides, and phase change material for high performance, compacted, and metasurface.